Hi again, and welcome to 7-2, Estimating a Population Mean. Key concept. The main goal of this section is to present methods for using a sample mean to make an inference about the value of the corresponding population mean. In this section, there are three main concepts. The point estimate. Point estimate is always going to be the sample mean. Use sample data to construct and interpret a confidence interval estimate of the true value of the population mean. And we're also going to find sample size, meaning that given some information, we want to find how many people we have to sample to get an estimate of the population mean. Some notation, most of it's not new. Estimate a population mean with unknown sigma. And sigma represents the standard deviation for the population. We know that mu is the population mean, n is the number of sample values, and x bar is the sample mean. Now we're going to add on to that our margin of error, which is E, and our sample standard deviation. This is not our population standard deviation. This is our sample standard deviation. And what are the requirements? The requirements are the same requirements that we had for the central limit theorem. The sample is a simple random sample, and either or both of these conditions are satisfied. The population is normally distributed, or n is greater than 30. We're going to see a lot of formulas here. I'm not actually expecting you to use them. I'm just showing them to you. I'm going to show you how to use StatGrind. I am going to explain what we have here. E is the margin of error, and we're using T sub alpha over 2. Instead of Z sub alpha over 2, and S is the sample standard deviation, and N is the sample size. And DF equals N minus 1. DF is the degrees of freedom. Then we have a confidence interval. It's a range of numbers used to estimate a population parameter. We want to estimate our population parameter, mu, but we don't know what it is. We're going to give a range, upper level and a lower level. We have a 95% confidence that our population mean is somewhere in this interval, which is the same alpha that I'm seeing right here, is the complement of the confidence level. The complement means 1 minus. If we're looking for a 95% confidence interval, that means that alpha, the confidence level, is going to be 0.05. We have this normal curve, and if I want a 95% confidence interval, the confidence level is going to be 1 minus 0.95, which is equal to 0.05. There's my alpha. But remember, we're going to split that in half. Why are we going to split that in half? Because we have this symmetry. We want this part of the graph and this part of the graph to be 0.025. Because if you add those two together, you're going to end up with 0.05. In the middle, if those two ends add up to 0.05, then what's in the middle is our range. And that's what we're trying to find. One thing we're going to do is we're going to find the critical value. Remember, what's the critical value? The critical value is the critical t-value separating an area of alpha over 2. Alpha is 0.05. Alpha over 2 is 0.025. In the right tail of the student distribution, this is the right tail. We could use the left tail, but we have to take the absolute value because t of alpha over 2 is always positive. The degrees of freedom is always going to be the sample size minus 1. Estimating a population mean with an unknown sigma. You're going to round it to what Pearson tells you to round it to. But in general, if we have original data and we're using data instead of data summary, then we round the confidence interval limit to one more decimal place than is used in the original. If we're given summary stats, then we just use the value that we were given. When using the summary stats N, X, and S, round the confidence interval limits to the same number of decimal places used for the sample mean. Now, there's some key points about this student t-distribution. We call it the t-distribution. A student t-distribution is commonly referred to as a t-distribution. And you'll see that we're using the t-distribution in StatCrunch. If a population has a normal distribution, then the distribution of t is equal to the sample mean minus the population mean. We don't have sigma for the population, so we use S for the sample divided by the square root of n. Again, we're not going to use these, but this is how things are calculated. Degrees of freedom. Finding a critical value, t sub alpha over 2, requires a value for the degrees of freedom. In general, the number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all data. For the method of this section, the number of degrees of freedom is the sample size minus 1. Key points about the student t-distribution. If we want to find the critical value, t sub alpha over 2, we can either use technology, which is what we're going to use, or we could use a table. And I do have a table here. This is what a t-distribution table would look like. If I had alpha over 2 is equal to 0.025. Down here, notice we have our confidence levels. These are the most standard, 90, 95, and 99. Here's our 95. And if we go up here, the right tail, 0.025. This is our degrees of freedom over on this side. Let's say we had 20 values in our sample size, then our degrees of freedom are going to be 19. We look here and we find 2.093 would be our 95% confidence level with 19 degrees of freedom. And technology can be used with any number of degrees of freedom. The table only had certain degrees of freedom. The student t-distribution is different for different sample sizes. The green is my standard normal distribution. The blue line is my t-distribution where n is 3. That's small. Now, look how much closer it gets to the green when I make n equal 12. That's why when it's 31 or more, we can just use our standard normal distribution or our z-tables. The student t-distribution has the same general shape and symmetry as the standard normal distribution, but it has greater variability. That means we need to make intervals bigger to make sure we get our information in that interval. That is expected with small samples. Key points. The student t-distribution has the same general symmetric bell shape as the standard normal distribution, but has more variability with wider distributions as we expect with small samples. What that's saying is, because we don't know the standard deviation for the population, we're going to make a little wider range for our mean to fall into. The student t-distribution has a mean of t equals 0. Just like our standard normal had a z equals 0. That was the middle. The standard deviation of the student t-distribution varies with the sample size, but is greater than 1. With a normal standard distribution, our mean is 0 and our standard deviation is 1. And as the sample size n gets larger, the student t-distribution gets closer to the standard normal distribution. The bigger the size of our sample, the more it's going to represent a standard normal distribution. This is a procedure that if you were doing it manually, you would have to go through. I'm going to tell you the parts that you have to go through for what we are doing, and we're going to use technology for some of it. Of course, we have to verify the two requirements are satisfied, that it's a simple random sample and the population is normally distributed, or n is greater than 30. It has to be a simple random sample, and then it could be either normally distributed or n could be greater than 30, or it could be both of those. As long as we have an unknown sigma, use n-1 degrees of freedom and use technology or a t-distribution table. With unknown sigma, we're going to use a t-distribution table to find critical values. And I'm going to show you how to do that in StatCrunch. Evaluate the margin of error. We're not going to be doing that. If we have a problem that needs that, I'll show you how to do it. Use the calculated margin of error and the value of the sample mean. Substitute those values in one of the formats for the confidence interval. I want you to understand it, even though we're not going to do it, but we will need it for some things. Here we have our bell curve, and here is our X bar. And then we're going to calculate our error. Let's say this amount right here is E. If I take X bar minus E, I'm going to be over here, aren't I? And if I take X bar plus E, I'm going to be over here. And again, this is E. My confidence interval is going to be from here to here. That's what this means. Our population mean, mu, is somewhere between X bar minus E and X bar plus E. And depending on what our confidence level is, that will depend on how wide that is or how small that is. Round the resulting confidence interval limits as follows. With an original set of data, round the confidence interval limits to one more decimal place than is used for the original data set. And when using summary statistics, round the interval to the same number of decimal places as used for the sample mean.